Thank you very much, and thank you so much for the organizers for inviting me. I feel honored, and it's a great opportunity to be here. So my name is Roland Molontay. I am from the Budapest University of Technology and Economics. I am an applied mathematician, and I work in the Institute of Mathematics. And I'm also the founder of a small, young research lab, the Human and Social Data Science Lab. So in this talk, I will introduce the activities of this lab and attempt to answer the question how data and network science can help to answer research questions in human and social sciences. So this is the outline of my talk. As I mentioned, I will start by introducing my lab, and then I will show you three examples. I will present a paper about the 20 years of network science. That's the title of the paper, 20 years of network science as seen through the co-authorship network of network scientists. Then we will turn to another project titled Content-Based Prediction on the Virality of Memes. So we will look at whether the dankness, the virality of a meme can be predicted using machine learning models. And then last but not least, I will talk about some recent projects about educational data science, so how we can answer questions arising in the educational domain, especially in higher education. So let's start with introducing my lab. So as I mentioned, this is a small and young research lab located at the Budapest University of Technology and Economics in the Institute of Mathematics. We say that our mission is to translate fundamental research in data and network science into lasting impact in social sciences and humanities. We are conducting both methodology-oriented basic research in network science and data science, and also applied research with a human-centered and societal focus. Our research areas revolve around four main topics. Network science, I will talk about that later. Educational data science, I will also talk about that later. And we also have two other topics that I won't have time to talk about, and maybe that's not that relevant at this conference: the health data analytics and intelligent monitoring, predictive maintenance, and anomaly detection. If you are interested in our work, you can find much more information on our website, the hsdslab.math.bme.hu. This is our team, so a small, young team, but we hope that we are expanding and become a larger team in the future. So next I will talk about this paper, the co-authorship network of network scientists, and I will talk about the past 20 years of network science without going into many methodological details. So rather superficially, I will provide a broad overview on this topic. So to start with, in this project, in this paper, we analyzed in some sense the past 20 years of network science. Why? What happened in the past 20 years? Basically, in the past 20 years, a new discipline has emerged, a new discipline that is called network science, a new discipline of great importance. Actually, network science was recognized as a new field of research by the US National Research Council in 2005, so quite recently in a sense. And in this 20 years, it has become a new discipline with its own journals. So there are the most prestigious companies, such as or publishing companies, have their own journals. For example, Network Analysis and Mining, Journal of Complex Networks by Oxford University Press, Network Science by Cambridge University Press, or Applied Network Science by Springer. And there are also conferences about complex networks, the NetSci, NetSciX, the Complex Networks conferences, and the list can go on. And there are also research centers and departments focusing solely on network science. So nowadays one can obtain a degree, a master degree in network science, in at universities such as Yale, Duke, Northeastern, or also at the Central European University, the CEU. So I just wanted to illustrate that now it's an individual new discipline, and why, what happened in the past 20 years that made it possible for network scientists to form a new discipline. Well, basically the prompt evolution of information technology opened up new approaches, new possibilities to investigate large networks, including but not limited to social networks, but you can also think of the World Wide Web, so how web pages link to each other, or brain networks, or protein-protein interaction networks, or infrastructure networks, and we can go on with this list. And in the first, the first questions were that how we can structurally describe these large networks. So at that time, approximately 20 years ago, the scientific community turned to questions such as what common characteristics these real networks have. And for example, scientists found, measuring real networks, that many of them have obeyed this so-called small worldness, also popularized under the name of 6 degrees of separation. So you can reach from if it's a social network and the actors are human beings, you can reach another human being in 6 steps. So the graph distance is 6, or approximately. Or the scale-free property, another very important property. It means that the degree distribution of the network follows a power law distribution. If it's too technical, the point is that there exist hubs. So there are hubs with high degree, with nodes with very high degree. So it's not a random network, but there are some more important nodes, so-called hubs. Another important structural property is the modularity, or the highly clustered nature of networks. So there are communities in most of the real-world networks, or fractality, the hierarchical structure of networks, and other properties. To understand these properties, also various network models have been introduced. So to understand and mathematically describe the structure, topology, the architecture of networks, you can think of the Watt-Strogatz small world network to understand the small world property of networks, or the Barabashi-Albert network to understand the scale-free property of networks. And recently, there is a shift from the structure properties to dynamics on complex networks and control principles on networks, and machine learning, data science approaches to understand complex networks. So in this article, we wanted to pay tribute to the achievements of network science, of the network science community in the past 20 years. Because approximately 20 years ago, or when this article was published, it was 2 decades ago, there were 3 seminal papers that were published around the same time. Then these 3 seminal papers, these 3 pivotal breakthrough papers, basically initiated this new field of research. These 3 papers are the paper about the small world networks by Watts and Strogatz in 1998. The paper about scale-free networks. You remember a scale-free network is when the power law, so the degree distributions follow a power law distribution, by Barabashi, Albert László Barabashi and Réka Albert, and in 1999, and the paper about the community structure of networks by Gervan and Newman in 2002. And in our article, we investigated network science papers in such a way that we wanted to see that so these are groundbreaking papers that received lots of citations. So here you can see in this figure that the Watt-Strogatz paper received more than 18,000 citations according to Web of Science. The Barabashi-Albert paper received more than 16,000, and so on, so a large number of citations. And we were curious that what can we say, so what influence these papers have on the science, on network science, and studied those papers that cite one of these seminal, one of these pivotal papers. And we are kind of proud of the fact that Stephen Strogatz, so that's the Strogatz from the Watts-Strogatz model, so one of the most prominent scientists in network science, also tweeted about our research, so we were kind of like happy about that fact. To clarify the terminology that we use here, so as I mentioned, we consider these three seminal pioneering papers that in some sense we regard as the roots of the rise of network science 2 decades ago. So we have these three papers, and that is just an arbitrary proxy, but that's what we are using in this paper. So we call a paper as a network science paper if it cites at least one of the three aforementioned groundbreaking articles. Okay, so and we call someone a network scientist. That is also kind of arbitrary. Of course, we are very much aware of that. We call someone a network scientist if they have at least one network science paper. So at least one paper that cites at least one of these three pivotal papers. Okay, so that's what we are investigating now. So these papers. We identified more than 31 network science papers, so that's the number of papers that cites at least one of the aforementioned three papers. And here you can see how the number of network science papers increased by years, and with respect to the country of origin, in the sense that with respect to the country of the first author of the paper, or so where the affiliation of the first author located is. And you can see that in the first few years, the United States was the leading country, but in 2008, China took over, and nowadays, so that's the cumulative number of papers, and in a logarithmic scale. So now China is the first one, USA is only the second, then UK ranks third, Italy, so that's the first from the continental Europe, then Japan, Germany, Spain, France, Brazil, and India. Okay, and in the other picture, you can see in what journals, so what are the most important, what are the most prominent journals of network science by year. So Physica A is now the most prominent one, so the highest number of network science papers are published in Physica A. Scientific Reports, that's the second most important nowadays. Physical Review E was the number one venue, number one journal of network science, but now it is just number 3. PLOS One, there were some years where PLOS One was the number one, so that's also good to know that where these network science papers are published. Then, after investigating these network science papers, we were more interested in the network scientists, so those authors who published these articles. So we built up the co-authorship network of network scientists. Why are we interested in a co-authorship network? Well, we are interested in research collaboration, because research collaboration is the mechanism, an essential mechanism to join together distributed knowledge and expertise into novel discoveries. So we somehow wanted to understand how the community of network scientists look like as seen through their co-authorship networks. So here, this is the co-authorship network. So one node here, so one node of the co-authorship network is a scientist, a network scientist. So you remember who a network scientist is in our terms. A network scientist is someone who has at least one network science paper. Okay? So we have more than 50,000 nodes, so more than 50,000 network scientists, and it was a very difficult task to identify the network scientists, because we used Web of Science data, so the source of the data is Web of Science, and that's not that easy to identify the authors. So there are no IDs. There are only the names, and especially for Asian names, that's very, very much difficult to understand that who is who. So we did in a half manual, half automated setup. We somehow cleared up the data. We do not claim that it is 100% clear, but at least good enough for our purposes. So just to have a picture of what is happening. Okay, so the average degree is around 12. So it means that an average network scientist has 12 co-authors with whom they co-authored another network science paper. So basically that's what it means. Here you can see the degree distribution of this co-authorship network. And what might be interesting, that the largest connected component, so we have more than 52,000 network scientists, and out of these 52,000 network scientists, 32,000 network scientists form the largest connected component. So there is a giant component, more than 60, or approximately 60% of the nodes are in one large connected component. So it means that from that connected component, everybody can reach. So any two scientists can be reached. There exists a path between them. So that's kind of surprising that despite the network science community is very diverse in the sense that from humanities, from brain sciences, from social sciences, physicists, mathematicians, and so on, still the community is kind of not that distributed or kind of connected. Okay. That's another network, the keyword co-occurrence network. So we had the keywords from the articles, from these network science articles, and there exists a link. Okay, maybe that was trivial, but I didn't emphasize that here in the co-authorship network, there exists a link between two nodes if the two scientists co-author the paper together. So here there exists a link, an edge between two nodes, between two keywords, if there exists an article where the two keywords co-occurred together. And of course, the edge weight or the width of the edge is proportional to the so how many times the two keywords were together, co-occurred together. So we can see that, and of course the size of the node is proportional to how many times that keyword occurred among the keywords. So that's not that surprising that that keywords such as complex network or network, scale-free, small world, community action, social network. So those are the most prominent keywords. So that means that, okay, this was a good enough proxy because these are really network science papers. So our proxy was somewhat worked. We can also observe that, okay, so for example, here we can see keywords that are more related to the mathematical nature of network science, so such as random graphs and network dynamics and things like that. Here, more social networks, social influence, homophily, community, and so on. So we can read some interesting things from this map, from this co-occurrence network. We also identified the most central authors from the co-authorship network. So we calculated the betweenness centrality, harmonic centrality, degree centrality. So if you don't know what exactly means, what these centrality measures exactly mean, don't worry about that. The thing is that somehow we can quantify how central, how important a node is in this network. And we also observed or also investigated how these centrality measures correlate with other scientometric indicators, such as the number of citations or age index, and you can see here the scatter plots. So we can if you're familiar with the network science community, you can find some you can find some big names here. Jürgen Kurz, he has the highest betweenness centrality and highest harmonic centrality, so a very central actor in the community in this co-authorship network, and also he has the second highest age index. Not very surprising that that your place in the network, or your role in the network, and your scientific influence or scientific measures, citation measures, are somewhat correlated. We can also find Albert László Barabási there, the famous Hungarian network scientist. So that's also something that we looked at. Okay, and so to sum up this line of research, we can say that despite the fact that network science has a multidisciplinary nature, we observe that a diverse but not divided community has emerged in the past 20 years, and we can say that we are convinced that the next 20 years will produce at least as many fruitful scientific collaboration as the last 2 decades, so we are kind of positive in this regard. Okay, and now let's move on to another topic, predicting the virality of memes. That's why is it important? What is the importance of memes? So Elon Musk tweeted 2 years ago, who controls the memes controls the universe. So 2 years ago, Elon Musk did not own Twitter, but used Twitter, and he tweeted that. So of course that's not necessarily true, but still it sheds light on the importance of memes. We can also observe an increasing importance of memes during the COVID-19 pandemic, because due to the social distancing measures, people turned more to the internet and had their social life in the internet, so memes were more important. And memes are actually studied extensively by the scientific community as well. Computer scientists, social scientists, scientists from marketing are all studying memes. Our research question was whether the popularity or the dankness, the virality of memes can be predicted based on its content alone. So we look at the meme, we read it, or a machine read the text, the machine looks at the picture, so text, image, memes, and whether we can predict that it will go viral or not. That's of course not an easy task for the machine, but let's see what we can do and what does it depend on. So what features, what attributes it depends on. I mean the popularity depends on. So that's what we did. We used advanced machine learning techniques such as convolutional neural networks, XGBoost models, and other sophisticated machine learning models to perform a content-based analysis of what makes a meme successful. So we engineered several features from both the text of the meme and the image data, and aimed at predicting the dankness on the content alone. We also looked at the question, what incremental predictive power image-related attributes have over textual attributes on meme popularity, and we scraped the data from Reddit, the front page of the internet, that's their slogan, during the COVID-19 pandemic. So this study also provides a looking glass into the thoughts of internet users during that time. So we scraped, using web scraping techniques, more or approximately 130,000 posts, memes. So those are image with text memes from Reddit, the memes subreddit. So that's one of the most prominent forum for posting memes. And we downloaded or scraped these memes at the beginning of the global coronavirus outbreak. So you remember 2 years ago, March 2020, so when the global coronavirus pandemic started. And we extracted a lot of features. I will talk about that later. But first, let's discuss what is our target. So as I mentioned, our goal is to predict dankness. But what we mean by dankness, basically the number of upvotes. So we can also observe that the distribution of upvotes follow a long tail distribution. So a power law, or more or less a power law distribution. It means that most memes receive only few upvotes, so those are not viral, those are not dank memes, and there are a few memes that received many upvotes that are 2 or 3 times in magnitude, 2 or 3 times higher than the rest of the. So there are viral memes. So that's a well-posed question to identify the viral ones, because there is a big difference between viral ones and non-viral ones, or dank ones and non-dank ones. So we translate this question into a binary classification task. We have this binary target variable, dank or not dank. Okay, so the top 5% of posts were classified as dank. These are the features that we engineered. We used the text, both the text on the, so the caption of the meme, the title of the meme, and also the text written on the meme. So there are, in a lot of cases, the text is written on the meme, so as a picture, as an image. So that's not that easy to see what or for a machine to understand what the text is. So we used optical character recognition to extract the text on the memes, on the image, then use tokenization, lemmatization, and stemming to understand what words are there, and extract some low-level text-related features, such as the length of the text, the sentiment of the text, and the topic of the text. I will talk about the topic later. So we can see whether the length contributes. So if it's a long text, it contributes positively or negatively to the virality. And not that surprising that people don't really like very long texts on the memes and things like that. Topics. So here you can, as I mentioned, it was created during the coronavirus outbreak. So you remember the toilet paper memes, I assume, and things like that. So those are the most prominent keywords here: coronavirus, COVID, toilet paper, and so on. So we, using some manual work, we created the categories so to provide a topic analysis, current politics-related words, or coronavirus-related words. So we grouped together these words to understand whether one topic is more popular than another in terms of memes virality. Okay, and we also extracted image-related attributes. We used low-level image-related features such as the thumbnail area, or the colors presented in the image, or the hue, saturation, and value of the image, and we can observe some interesting findings. So, for example, the more popular memes tend to have larger thumbnail areas, or value shows a slight positive correlation with dankness. Hue and saturation show a slight negative correlation with dankness or with the uploads. That is more interesting that we also extracted high-level image-related attributes. What I mean by that, we tried to describe the semantic meaning present in the image. So these were not semantic meaning, the colors and thumbnail areas, so low-level features. Here, let's say high-level features. So we used a neural network, the VGG16 neural network, to identify objects present in the meme image. So, of course, it works with confidence. So, for example, here it identifies that it's a toilet tissue with 62% and things like that, but it works reasonably well. And so we can also identify what the meme is about using this method. So what the picture or what the image is about. That is also not that surprising that some of the top categories related to the culture around the COVID-19 pandemic, so the toilet paper memes and similar. So after we have these features, after we have these variables attributes, we can train our models. We train the gradient boosting and the random forest model to perform this binary classification task. And the message is, or what we found, our observation is that these models somehow can predict, or to some extent, they can predict the virality. But this is so it is AUC score. That's a performance metric of machine learning models. That's not very high. So that's not very surprising. It's a very difficult task to identify dank memes. So the machine learning models could not do magic here, but in some sense they can be used. And this research also sheds light on what features are important. That was surprising that some simple features such as the text length and the image size showed great importance for predicting the virality, and some colors are also important. So people prefer darker colors in memes, for example. What we also saw that what incremental predictive power text-related and image-related features have on each other. Not surprising that they both have some additional incremental. So solely on the text or solely on the image, the performance of the model is worse than combining the two families of variables. So the conclusion is that the content-based analysis can predict success with reasonable efficiency, but of course more is needed. So for example, in the future, what we could not do is to understand whether a meme is humorous or not. But that's the point. So, but that's very difficult for a machine to understand sarcasm and understand the humorousness of the meme, especially if it's not only text and not only image, but the two. So in some cases, the humor comes from that. Okay, what is in the text and what is in the image is unrelated or just the opposite, and that's kind of difficult. But that's what we are doing now to extend this research in this direction to understand the point, the humorousness of memes. Okay, and last but not least, I would like to tell you something about our educational data science projects. So educational data science, of course, there is a great potential in educational big data. Neptune, if you're in the Hungarian higher education system, you are all aware of that. So, but I assume that in other countries there also exist some some educational or higher educational data, administrative systems where you store the data of the students, of the professors, of the grades and whatever. And at BME, at the Budapest University of Technology and Economics, we established a connection between a collaboration with the Central Academic Office. So at ELTE it is called the TEO. At BME it's sorry for those who don't understand. So that's just the academic office or the study who are responsible for the study register. And our goal was to support educational decision making based on the big data stored in these educational administrative system. Of course, this project raises a number of issues because we are working with personal data. So, of course, all the data that we have access to is anonymized. So we don't know who the student is. That is just an identifier that cannot. So it's anonymized. And we also signed a strict NDA, a non-disclosure agreement. And that's research is totally in line with the strict regulation of the European Union, the GDPR. So now I will show you some examples. So for example, we looked at the predictive validity of the university entrance score. So in Hungary, the university admission system works like that. Students has a preference ranking on their on the desired university programs, undergraduate programs. So that's what is denoted here, that this girl wants to go to this university, that's rank number 1 for her, this rank number 2, and so it has a preference ranking. And universities or programs also have a preference ranking of the students. That is the students that I want the most, that is the students that I want the second, and so on. Now we understand what the preference ranking of the student is based on. Its own preference. They talk about in the family, with friends, and they have a preference. So we don't care about that. That's what they think, where they want to go. But what the preference ranking of the universities is based on, so how universities or programs rank students, well, they rank students based on the university entrance score. In Hungary, the university entrance score is nationally standardized, or we have just moved from a nationally standardized to a university-defined one, but this study is based on the system that is existing right now, so it's a nationally standardized process. So we are curious whether this ranking is a fair ranking. It has a good predict. What do I mean by fair ranking? Of course, that's kind of a gray area. What do we mean by fair? Here, we mean fairness, that a ranking is fair if it can efficiently distinguish between future dropouts and successful students, right? So, okay, one can argue that that's not the only goal of a good entrance score, but that's what we are looking at. So for example, here you can see this is data from my university, the Budapest University of Technology and Economics. So here you can see the admission point score given intervals. So if you look at this picture in a colorblind setup, this is just a normal distribution, not that surprising. Okay. And what the colors are, it means that in this region, so if the student has an admission point score between, I don't know, 380 and 400 or whatever, then 39% of them are successfully graduating, and 61% of them drops out from the school, from the university. Budapest University of Technology and Economics has an issue with the dropout rates. All higher education has an issue, but especially STEM education, so engineering, maths, and things like that. Okay, that is happening. So what we found that the current university, nationally standardized, nationally defined university entrance score overestimates the performance of male students. So if we have two students with the very same entrance score, and one of them is male and one of them is female, then the female has a higher chance of graduating and a higher chance of performing well in our university. High school grades have strong predictive validity. I'm not sure how familiar you are with the current university entrance score, but basically it has two main components, the high school grades and the mature exam scores. Or the mature exam, the high school leaving exam, A levels or something like that. And the high school grade component has the stronger predictive validity. That's important. And general knowledge is more important than program-specific knowledge. So that's a technical school. I'm coming from a technical school, an engineering school, basically. But still, and I hope you will be happy about that, the scores, the grades in humanities, so what you scored, what grade you had in Hungarian or in history, have a high incremental predictive power over the maths, over the physics, over the IT, informatics, and so on. And we also found that the predictive validity can be improved by slight changes, for example, over-representing high school grades. Unfortunately, this is not the direction that we took, but I mean, the universities in Hungary, but still that's what we found. We also investigated whether using machine learning models we can identify students at risk of dropping out. As you can see, we have a pretty high dropout rate, so that's important. So that's also a binary classification task using the historical data. We would like to distinguish between, you would like to find the patterns, distinguish between those students who are at risk of dropping out and those students who are fine. As early as possible, so based on the data available at time of enrollment. And we found that these models have a pretty good performance, so at-risk students can be identified efficiently solely based on the data that is available at the time of enrollment. So what data is available at the time of enrollment? Basically, some personal data, what was the high school of the student, and so on, and the data that forms the university entrance score. So the high school grades, the maturity exam results. So yeah, basically that. If we include the first semester data, so not only we do not build our model solely based on the data available at the time of enrollment, but we complement that using first semester data. Not that surprising that, of course, the predictive performance can be increased. How to interpret a model? So that's not only our goal to say that, okay, you will drop out, but we also want to say that, okay, why? What are the reasons? What features contribute negatively or what attributes contribute positively to the prediction? That's called interpretable machine learning or explainable AI. So to measuring the marginal contribution of the variables on the prediction. We use this game theoretical approach, the Shapley value-based approach, without going into technical details. So for example, here we can see 3 students. So these 3 rows correspond to 3 students. The first row corresponds to an at-risk student, because here our output is just 0.16. It means that the student has a low probability of graduating. Why? And here we can see with color blue those attributes that push the prediction lower, so that contribute negatively to the prediction. So the fact that their mathematical exam score was only 62%, the fact that their science high school science subject was the average grade was only 3.5, and so on, they contribute negatively. On the other hand, that this years between variable, it means that it measures that how many years elapsed between the high school graduation and the enrollment in higher education. So no gap year, it means no gap year. The fact that the student had no gap year contributes positively to the prediction. So it pushes the prediction higher. Here, a good student, we can see that almost all the factors contribute positively. And here, a borderline student, what are the negative, what are the positive factors? Okay. We also show together with the Department of Psychology whether if we not only use these the grades and exam results, but we also see the predictive power of psychological factors, whether using the psychological factors we can build a better model. So whether these psychological factors have some incremental predictive power over the grades. And so all the rest of what I have shown you, it relies on basically every student. So thousands, tens of thousands of students, because we have the administrative data in the administrative system, and then we just build the model. Here, that's not the case. Of course, we do not store any psychological factors regarding the students. So using survey data, here the number of students who participated in this survey is much lower. So it's not tens of thousands, but also only hundreds of students. But still, big enough data to play with. So we found that using an appropriate set of psychological measures, the dropout, the university performance can be predicted significantly better than solely relying on the grades, and especially coping proved to be the most important psychological factor or personality trait that sheds light on the importance of stress management for university students. And the questions, of course, comes up how to use the results. We have a sophisticated machine learning algorithm that, okay, let's say efficiently predicts whether you will drop out or not. And what? what is it good for? Of course, that's not a good utilization if on the 1st of September, the school starts, we go to the student after they signed the paper that now they are a university citizen. Okay, congratulations, welcome to the university, but we have some mathematicians and they built a sophisticated machine learning models, and I'm very sorry to inform you that our machine learning model predicts that you won't be able to graduate successfully. No, of course, you are laughing, and that's good because, yeah, of course, that's not a good utilization. But I assume you can argue that there exists some good utilization. So we can think of that how. But after thorough consideration, if we recommend a remediation course based on what we found, or some personal guidance, or some targeted development program, so it can be used. And I want to, maybe I will tell you that, and then I will stop. So that's another interesting piece of research, also from the educational data science domain. Our question was whether professors can buy better evaluation, student evaluation, with lenient grading. Why is it a question? We observed that not only us, but all over it's true all over the world, that grades are increasing recently. So this is two leading universities in Budapest, my university, the Budapest University of Technology and Economics, and Corvinus University. And here you can see that grades are increasing on both universities, at both universities. I assume that here at ELTE as well. I don't have data, but we can check if you're interested and connect me with the right person. So and the question is why? Of course, the question or the possible solution is that there might be an increase in student ability. So grades are increasing, okay, and then you are saying no. And of course, well, I don't, we doubt that. Maybe, but maybe not. And another possible reason that simultaneously, so in the same time period, student evaluation of teaching, so SET, rise to prominence. So basically every university all over the world has some kind of student evaluation of teaching system. And at many universities, they are also used for promotion, or especially in Western Europe and in the United States, used for promotion or higher salary, or your bonus is based on student evaluation of teaching, and something like that. So professors, university lecturers are incentivized, are motivated to increase their student evaluation of teaching score. How can they do that? Well, that's the right way and the difficult way to improve their teaching. That's good. But there might be another thing, that they try to buy better evaluation with grading leniently, and they might hope that students will be grateful for that. And that's the question whether this phenomenon exists, or so this research does not tell us anything about the professors. This research tells us something about the students, how students react. Okay, and let's see. So here we can, on the x-axis, here we can see the grade, and on the y, so 1 point is a course, is a section, and on the y-axis you can see the average grade and the average SET score, and we can observe a high positive correlation. But this is not enough for us, of course. Looking on a correlation or a scatter plot is not enough. It might be the case, of course, and we hope that that's the case. We will see that how it works. But okay, let us assume that this is because there are some professors who are teaching effectively, efficiently, who are good teachers, and that's why they have good they have good grades. So the students have good grades on their class. Why? Because this professor teaches efficiently, and if they teach efficiently, then students will get good grades. And because he is or she is a good teacher, that's why they receive a high student evaluation. So there's no direct causation, but a common cause. And that's what we are trying to control or account for this unobserved teaching effectiveness. So teaching effectiveness is not measurable, or at least we don't measure that, or we don't observe that. So we don't have measures like that in the data. But using sophisticated econometric methods, such as fixed effect regression and two-stage least square linear regression, we can somehow control for that. So without going into technical details, just what is the idea behind the fixed effect regression? So the assumption is that in a small time frame, small time period, so let's say 4 semesters, so we assume, that's an assumption. All models have an assumption. So the assumption is that in 4 years, or in 4 semesters, the teaching effectiveness, the teaching ability of a professor is rather constant. So in a small time, it's rather constant. What can happen? It can happen that in 1 semester, the midterm or the exam was easier. It happens that when they wrote the exam, it was easier. So that's why teaching effectiveness remained constant, but the exam, the midterm, was easier. So the grades differ. The teaching effectiveness is constant, but the grades differ. And we can see how students react to that change. Okay? And to cut a long story short, all estimates are between or around 0.3. So it means that on a 1 to 5 scale, so everything is on a 1 to 5 scale. So the grade is on a 1 to 5 scale, and the SET score is also on a 1 to 5 scale. So in average, ceteris paribus, so all the other factors remains unchanged. If you increase the average grades by 1, then you will receive expected value 0.3 higher student evaluation. So some kind of effect. We can observe some, not very big or not enormous, but some effect we can observe. And maybe I just stop here. There are also other things, but I don't have time for that. So thank you very much for your attention.